going to start today's lecture, right? So see, we are going to see about the isomerism in alkenes, right? What has been taught in the last class? Can you tell me? Okay, no problem, Vishnupriya. Okay, no worries. We will be starting from here. Isomerism in alkenes, right? So first of all, structural isomerism. Are you comfortable, guys? So in structural isomerism, chain isomerism will be there, right? So chain isomerism. See here. What will be there in chain isomerism? What is saying here? The isomer differ with respect to the chain of the carbon atoms, as in alkenes, ethene, C2H4 and propene, C3H6 can have only one structure, but alkene higher than propene have different structures, right? So higher than propane, there can be different structures can be there, right? So we can change the structure of the alkene group, right? Let's suppose greater than 3 carbon, 4. Let's suppose you are having 4. We can change the structure of this carbon and we can put here, right? And we can attach any double bond in this between two, right? Let's suppose we are having what? Butene 1 ene. So double bond is here, right? We are having double bond here. Now what we can do here? We can change this CH2 group. We can change this CH2 group and we can remove this double bond and we can change this CH2 group and make CH3 as well. Yes or no? Getting my point. What is saying here? The isomer differ with respect to the chain carbon atom, as an alkenes, ethene C2H4 and propene C3H6 can have only one structure, but alkenes higher than propene have different structures. Alkene having molecular formula C4H8 as two chain isomers. See here. So we can see here how we can draw the alkenes. Any doubt to anyone? We can just change what? We can change the number of carbon. Our last carbon can be joined with this carbon. We cannot join with this. If you are joining with this carbon, again it is a straight chain, right? It will be coming in a continuous chain. So it will not be a that is isomer. You have to put either here. You have to put here in middle. Take my point. So 2-methyl propene will be there. Here there will be a double bond will be there, guys. So find out where there will be a double bond. With this carbon, with the CH3 is there, let's suppose. CH is there. And again, what is there? CH3 is there. Fine. Now, if we are putting double bond, so there will be a 5 bond will be there, right? But CH2 can be there. So this hydrogen will be removed from here. There will be no hydrogen will be there, right? So it will be what? The carbon and number of hydrogen. Please find the carbon number and hydrogen number. Is that okay? Is that okay or not? Here there will be no triple bond. Will see the 2H will be there. So 2H here, 3H here, 5. 5 plus 3, 8. Getting my point? And how many hydrogens are there? C4H8 is there. So these structure and these two structure both are what? Chain isomers. Here there is change, guys. So we can change here. What? We can make this hydrogen. We can remove this hydrogen and we can put double bond here. And CH3 has been changed here. So this will be what? Isomer of this structural isomer. Now we are going to see about the position isomers. The isomer differ in the position of the double bond. If double bond position is shifting, right? Let's suppose you are seeing here double bond here, right? So what we can change? What we can change here, guys? Please check and please then tell me. Although we have seen the position isomer in case of the alkane as well. Now you have to see here the isomer in the alkene in case of alkene as well. See here, can we change the position of double bond? Then only it will be called as what? Position isomers. See here in this case, with first bond, there is a double bond, right? But this is wrong one, right? We have to keep what? We have to change this double bond and we can do here. Getting my point? Accordingly, you have to check the number of carbon and hydrogen as well. Because if their positions are changing, there can be a difference as well. So see here, this is CH3, CH3, CH2, CH, double bond, CH2, right? Now I am making this CH3, CH, right? Then again CH, CH if I am making, right? So here there will be a CH. And double bond if I am making, then I cannot put CH3 here, right? And this will be not. We have to do what? We can do what? We can first change the position of double bond. We can change the position of double bond from here to here, right? It has been changed. And accordingly shift the number of hydrogen. Where there is a requirement, put the hydrogen accordingly. Getting my point, everyone? Yes or no? Yes or no? Please tell me, guys. Is it easy? No. The geometrical isomer is shown by alkenes, the compounds which have the same structural formula but different in spatial arrangement of atoms or groups of atoms about the double bond are called geometrical isomers, right? The phenomena is known as geometrical isomerism. The geometrical isomerism is exhibited by certain members of alkene family that we are going to see now. See, in this case, what you are seeing, double bond is there, right? So double bond means what? There will be no change. We cannot rotate, right? In case of alkane, we can rotate because if you will fix this, this can be rotated, right? This can be rotated. Either this can be also rotated. But here, if there will be a double bond will be there, so there will be a rotation will be there. A rotation will not be possible there, right? So in this case, you can see here the rotation is not possible. Is it fine? Now cis and trans. We are going to see what cis and trans. A and A both are in adjacent side, so it will be what? Cis. B and B both are in same side, so it will be what? Cis. So you can see here we have made a picture very beautifully. This is what? A and A. This is what? In adjacent side. B and B in adjacent side, so this will be what? Cis. Here you can see B and B opposite side, right? 180 degree. So it will be what? Trans. A and A is an opposite side, so A and A opposite side. Opposite side. So this will be what? Trans. I hope everyone is clear with this cis and trans. Cis and trans, guys, clear? Now check here. We know that a double bond consists of sigma bond and pi bond. We are knowing that if a carbon-carbon bond is there, so here it will be one sigma and one pi will be there. Due to the presence of pi bond, the group or atoms attached to each sp2 hybridized carbon atoms cannot rotate. That I have told you guys, right? They can do so only by breaking the pi electron. So until unless the pi bond is not broken down, so there will be no rotation will be there, right? So therefore rotation about the double bond is restricted or hindered. Because of the hindered rotation, the molecule of the type C2A2B2 exhibits two space isomers which are called geometrical isomers. So there will be what? Geometrical isomers will be there because they are restricted rotation, right? The isomers in which similar atoms or groups lie on the same side of the double bond is called cis isomer, and different will be called as what? Trans isomer that we have seen. Clear, everyone? The cause of geometrical isomer. Why there will be a cause of why there is a need of this geometrical isomer? See, the isomer in which similar atoms or groups lie on the same side of the double bond is called cis, while the other in which they are displaced on opposite side are called trans. That we have seen, guys. So geometrical isomer is also called as what? Cis and trans isomer. That also we have seen. Condition for geometrical isomerism. The main condition of geometrical isomer are what? The molecule must have double bond. So C double bond C. The two atoms or groups attached to the same carbon atoms must be different. Getting my point? So two atoms, that is what? CH3 or H. They are different. So they must be different. Clear? Any doubt? The two atoms or groups attached to the same carbon atom must be different. We will be seeing here. See here. The two atoms that are attached to the carbon are different. Here H is there, CH3, CH2 is there. So here H and H is there. So it's not geometrical isomerism. This is what? This is not geometrical isomerism. This is not geometrical isomerism. Getting my point? Easy? Getting my point, everyone? But see here, H and Br, they both are different, right? So this is what cis. They are adjacent one. They are adjacent one. This is what trans. Hydrogen and hydrogen, opposite side Br and Br is what trans. So condition for this cis and trans got, guys. Whether it will be a geometrical isomer or not, have you got it? Yes or no? Please tell me, guys. If same will be on the same carbon, then it is not a geometrical isomer. Different groups should be attached with one carbon. Then only it will be a cis or either trans isomer will be there. Clear? So same side will be there, then it will be a cis. Opposite side will be there, then it will be a trans. Clear, everyone? Any doubt to anyone? Easy? Now we are going to see another example. See here. Is this a isomer or not? This is not geometrical isomers. Both are same. Both are same. So no geometrical isomerism. But see here, this is geometrical isomerism. See here, COH group, COH group. This in the same side. This is cis. Opposite side, trans. Hydrogen, hydrogen. Opposite side. So C double bond, C, COOH. Here H is there, and here H is there. Again COOH is there. So it will be what? Trans. Clear? So what will be cis for this? Carbon double bond carbon, and here it will be what? COOH. Either upward or downward, there is no problem, guys. But here H and S should be there. Clear? So geometrical or cis trans isomer is also shown by alkenes of the type what? XYC. That is equal to CXZ. We will be seeing these things in the later part, right? Clear, everyone? With this part, are you clear or not? Please tell me. So any doubt to anyone? No? Now come to see this part. Cis isomer is more polar than trans isomer. That we have to keep in our mind. Cis is more polar than trans. And how we can check the polarity, that way we will be showing you, right? So here, dipole moment of cis dichloroethene is 1.90. Dichloroethene, right? Cis dichloroethene. And while that of trans form is almost 0. Trans form is almost 0. Why this is almost 0? See here, Cl and Cl, they are more electronegative, so they will be cancel each out. See guys, they are at, you can say that they are at 180 degree. Yes. So if they are in opposite direction, so they will be cancelled out. So their 180 degree will be there. Actually, how we are finding the dipole moment? Do you know, guys? We are having certain formula for finding this dipole moment, right? And it is, you might have learned the vector addition of, that is what in physics you might have learned a square plus b square plus 2ab cos theta. That is known as what? Vector addition of that is rectangle addition of vector, right? Where you are getting the resultant a square plus b square plus 2ab cos theta. In the resultant form, you are getting what? That you are getting in the resultant addition of vector when you are adding the two. If you have to get the resultant vector, so you are doing this formula. Under root will be there. Under root a square plus b square plus 2ab cos theta, right? So here the angle will be 180 degree. So if 180 degree angle will be there, so what is the value for 180 degree? Cos 180 degree is what? Knowing anyone? So guys, actually what will happen, this whole will become what? Actually, this will be cancelling out, so it will become 0. So it is what? You can see as 0, almost 0, right? But here you can see again cis, there will be more, trans, there will be 0. Getting my point? So cis isomer will be always having more dipole moment than the trans isomer. Clear everyone? No. Cis isomer has a higher boiling point than the trans isomer. So cis will be having more boiling point than the trans isomer, right? Now, third point is what? In case of solid, the trans isomer has higher melting point than cis isomer. This may be attributed to better symmetry of the trans isomer, due to which the trans solids fit very well into the crystal lattice. Therefore, trans isomers have high melting points. So in solid case, trans isomer will be having more boiling point. Cis isomer have higher refractive index than trans isomer. The stability of trans isomer is more than cis isomer. So you have to learn this, guys. So trans isomer is more stable than cis isomer. Now, we are going to learn the another type of isomerism where there is what? EZ system of geometrical isomerism. Actually, this is a part of what? Geometrical isomerism. Getting my point? Geometrical isomerism. This is a part of what? Geometrical isomerism. Any doubt? This is a part of what? Geometrical isomerism. Fine, everyone. So what we are going to see in this geometrical isomerism? See guys, what we are going to see in this geometrical isomerism? When there are 3 or 4 different groups attached to the carbon atoms, 3 or 4 groups are attached to the, different groups are attached to the carbon atoms of double bond, it becomes difficult to assign cis and trans designation of 2 isomers, right? To overcome this problem, a more general system of geometrical isomer called E and Z system was devised. Clear? So now we are going to see what? E and Z system. The E and Z system is based on the assignment of properties to the atoms or groups attached to each carbon of the double bond. The priorities can be assigned on the basis of rules given by the, that we will be seeing here. How that will be assigned? This is what? Carbon. There is what? Different groups are attached, right? So how we can see that whether it is E system or it is Z system, that we are going to see. So the very first rule is what? If the 4 atoms to the double bond carbon atoms are different. So that is what? Let's suppose fluorine, chlorine, bromine, iodine is there, right? Now, so priority depends on the atomic number. So which is having the highest atomic number? I hope everybody is clear with this. Iodine is having the highest atomic number, right? So the atom with the higher atomic number gets highest priority. For example, if the 4 atoms attached fluorine, chlorine, bromine, iodine, the priority becomes iodine, then bromine, then chlorine, then fluorine, right? If 2 isotopes of the same element are present in the isotopes of higher mass number, gets the higher priority. For example, deuterium and hydrogen is there. So deuterium will be getting the priority because deuterium is having higher mass. Getting my point? Now, if 2 atoms are identical, the atomic number of the next atoms are considered for priority assignment. So if 2 atoms are identical, then next atom will be taken as for the priority. For example, CH3, C2H5 are attached to C2H5 gets priority. So C2H5 will be getting the priority because they are having the more mass, you can say, right? So gets added because atoms to the first carbon atom is CHH, where CH3 group is what? Having HHHH. So the C2H5 will be getting the more priority. So you have to learn these priorities, right? Where there is a double bond or triple bond, both atoms are considered to be duplicated or triplicated. So that we are going to see here. So see here, carbon A is A. See here, carbon AC and C equals, then what will be the priority that we are going to see, guys? Please try to understand here how we can give this priority. Here A equals, right? Then what we are going to see? A equals, then CA and AC, and C equals what? A. So we are going to give this priority. We will be doing with some examples, right? Here we are having what? RCOOR. So how we have given the priority? R, CO, OC, and R. And R, C triple bond N. Then we have given what? R. We have designated this 3N, right? N, 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 N. So R, C, and N. Getting my point? Now, EZ system, if two higher priority groups are on the same side, the double bond of the double bond, the isomer is called Z. That is German Jasmin, meaning what? Together. So if what is saying, if EZ system, if the two higher priority groups are on the same side, higher priority group, so we have to first find the higher priority group. So if higher priority group are on the same side, then EZ system, if two higher priority groups are on the same side of the double bond, the isomer is called what? Z. So it will be called as what? Z. Clear everyone? And two higher priority groups are on the opposite side, the double bond, the isomer is called E. So if two higher priority groups are on the opposite side, then it will be called as what? E. So Z and E are clear to each and everyone. Now, see here. So higher priority group, same side, low priority group in the same side. So it will be called as what? Z. Now, so now see here, CS3, CS3. The higher priority group on the same side. So it will be what? Z. Higher priority group and higher priority group are on the opposite side. So it is what? E. Clear everyone? Here F, here Cl. Both are what? I and Cl. I and Cl both are on the same side. Both are the more, atomic number is more. So they are what? Sorry, not Cl. I and B are on the same side. I and B are on the same side. Then it is Z. Here you can see here it is what? Here there is a mistake is there, guys. We have to change this, right? So how we can change? How we can change? How we can change? Can anyone tell me? Where should I put? Where should I put, guys? Please tell me. Can anyone tell me? I hope everybody is understanding this question now. Any doubt to anyone? If ClBr is there, right? So Cl and I should be on opposite side. For what? For E system. If Cl and I is on the opposite side, will that be what? Will that be E or not? Please tell me that. See, guys, I and Br are on the same side. I and B are on the same side. Then what is the order? I and B are on the same side. Then it is what? Z or E? Guys, see here. I and B are. I and Cl. If they both are on the same side, then it is what? Then we have to take what? That they are what? Z. If that I and Cl, they both are on the they both are on the opposite side, then it is what? E. Getting my point? Clear everyone? I'm taking one another example. Let's suppose we are having what? CS3. Let's suppose I am having one another example. Then I hope you will be able to understand more. Say this group. CS2, CS3 is there. Clear? And CS3 is more than H. Clear everyone? So this one and this one more in priority. So they are having what? Z. Clear? And you can see here, what? They both are on opposite side. And now they both are on same side. So what we are having here? This is what? E. So we have to prioritize the group first. The atoms or groups of the higher priority are shown by bond colors. So here is no any bond color is there, but I am telling you about this. There should be like this. Clear? Yes. So we have seen this. Now do this question and tell me, like, if there is any discrepancies there, then please tell me. Guys, please note this question in your notebook and try to find the answer from your side and then tell me. See, find the in first carbon, which one is priority? Fluorine. In the second carbon is what? In the second carbon, if you will be going to see, then Cl is in more priority. Clear, everyone? Then they both are on the same side. So Z, if they will be on the different side, it will be what? E. Now, we are going to see the stability of alkenes. Guys, have you seen the preparation of alkenes in the last class? Yes or no? Please tell me, guys. Preparation of alkenes. Okay, good. Now see here. Okay, who will tell me why I have taken the priority chlorine, not C2H, not CH2CH3? Can anyone tell me? Can anyone tell me why I have taken the priority Cl, not CH2CH3?
Sir, I'm audible, sir. So it is because of halogens are prioritized before alkanes, sir.
Apart from this, is there any reason? Yes. See, I have told you in the starting of the class, right, that first take one carbon, right, and check the two groups that is attached, which one is having more, like, which one is having more atomic number. Yes, Anil, very good answer. So in this C is directly attached. So carbon is having more atomic number than H. So it is more in priority. Yes. Getting my point. And here Cl is having more atomic number. So they are in the same side. Clear? Getting my point? In this case, hydrogen and fluorine is more atomic number. Chlorine is more atomic number. They are in the same side. So these are what? Z. They are in the opposite. Then it is what? E. Any doubt to anyone? Guys, high priority group, low priority group. If you are not knowing this high priority group, so you have to understand first this. High priority group will be what? Priority will be based on atomic number. Atomic number. Clear? Doubt? So we have seen all these things. Now, stability of alkenes. See, the relative stability of alkenes can be determined by comparing their enthalpies of hydrogenation. Enthalpy of hydrogenation is heat evolved when 1 mole of alkene reacts with hydrogen, right? For example, we are having what? Both geometrical isomers of both butene consume 1 mole of H2 and produce the same product butane upon catalytic hydrogenation in the presence of catalysts such as platinum or palladium. Clear? Any doubt? Any doubt to anyone? See here. So we are having what? Carbon, CH3, H is there, C double bond C is there. So this is what? If catalytic hydrogenation means what? In the presence of H2 and PD. So double bond will be break down and there will be what? Single bond will be there. Getting my point? So you can see here, this is what? Cis one and this is what? Trans one. And we have also, I have told you in the starting that trans is more stable than cis. Clear? What do you say, guys? What do you say? One more thing, trans isomer has 5 kilojoule mole energy less and hence more stable than cis. More energy means less stable. More energy means less stable. Less energy, more stable. If I will talk about you guys, you are having really very good energy. So you are not stable. You will be finding someone for you. The people are having more energies, they are finding someone for themselves, right? But if you will look into your, grandfather, grandma, they are old now, right? So they will be not looking into anyone, right? They are having very less energy. Oh, beta, I will not be able to walk. Generally, this happens with our grandma and grandpa. They are not able to walk. They are not able to, do anything. So they are having what? Less energy. But they are more stable. Why? Why? Because they have earned so much money. This is just for the example case I have taken, right? Don't take it otherwise, guys. So this is what? So if in chemical reactions also, if the molecules is having higher energies, it means what? They are less stable. Lesser energy will be having more stability. Yes, Vishnu Priya, you are looking good. Yeah. Is there any mirror in front of you? Yes. Yeah, yeah, I know. The girls love mirror, right? Like after their parents, if there is anything for to love, that is mirror. And one for mirror and one another thing that is makeup kit. I know well.
Sir, I don't have any mirror in front of me, sir.
Yes, where is your mirror?
I don't have any mirror in front of me, sir.
Okay, okay, no problem, no problem. If it is happening also, then also there is no problem, right? See, we have everybody wants to look good, right? So if you are also trying, then what's bad here, right? So it should be there, and it must be there, right? Everybody should should be looking good. So if you are looking, then it's good. No worries. Okay, Vishnu Priya. So
Yes, sir.
yeah, don't worry. Okay, continue. So guys, please concentrate here. So which will be having more energy, guys? So trans will be having lower energy. Cis will be having more energy. So we can see in the graph that what? So trans is having lesser energy, so it will be more stable, right? Clear, everyone? Any doubt? So why we are saying that trans is more stable? Because they are having the lesser energy in comparison to what? The cis one. Now, steric hindrance or steric strain. What is the meaning of this steric hindrance or steric strain that I am going to tell you? See guys, any bulky group is present in here. Like let's suppose CS3 is there, right? And this carbon can make another CS3 group, right? So with this carbon, if hydrogen will be there, see CS3, the molecular mass will be so, very high. So it is, you will be learning in 12th standard as well. If these two group will be there, so more steric hindrance will be there. If I am drawing, instead of the CS3, if I am drawing a 2H, less steric hindrance will be there. This is one case. Now, we are having what? Alkene in the same side if carbon is there, right? Carbon is there, CH3 is there, CH3 is there, right? So there will be what? In the same side if two, more molecular masses group or more, you can say that more bulky group will be there, then it will be having the steric strain. It is known as what? Steric strain. But if they will be in the transform form, like here, if I'm drawing CH3, and here there will be CH3 will be there, here there will be CH3 will be there, then it will be having very less effect of the steric hindrance or no steric strain will be there. Getting my point? So enthalpies of hydrogenation shows that the stability of alkene also depend upon the position of double bond. For example, enthalpy of hydrogenation of some alkenes are shown here. So stability will depend upon this as well. Guys, are you clear with this? So if trans will be there, then also more stable. If steric hindrance will be there or strain will be there on the in the trans form, then there will be no steric strain. But in the cis form, in the same side, if these two group will be in the same side, it will be having the more strain. Getting my point? Clear? Any doubt? Now see here. Transbuted 2-methyl butene, that is delta H naught is what? Minus 112.5. And here what is what? 2,3 dimethyl butene. Delta is 11.5 kg. So more the energy, lesser the stability. Now see here. The above data indicate that alkene become more stable with increasing substitution. In other words, the greater the number of alkyl group attached to the double bond carbon atoms, the more stable is the alkene. Guys, if more R will be attached, more stability will be of their alkene. So you can see here. Here there is 4R is there, 3R is there, 2R is there. So more stable like this. There. Any doubt to anyone? Guys, any doubt? Now, see here. We are having again what? 2R and H. 2R on the opposite side. Now, we are having what? 3H. So you can see here, see, these two are on the same side. This is what? Cis form. These two are on the opposite side. These are what? transform. Getting my point? So more the number of R, more will be the stability, right? No. But here you can see that there are 3 H's there, but 1 R is there. So this will be more stable than this. Here there is no R is there, only CH2 group is there, then this will be more stable than this. Clear? Any doubt? Now we are going to see the preparation of alkenes, guys. There are several methods to prepare this alkene. So you might have seen the preparation of alkenes in the last class. Now today we are going to see the preparation of alkenes. Any doubt to anyone? Now see here. See guys, alkenes can be prepared by the following methods. The first one is what? From alkyl halides or haloalkanes. Alkenes can be prepared from alkyl halides, usually bromide or iodide. So alkyl halides, guys, alkene can be prepared from where? So from alkyl halides. What are these alkyl halides? Like CH3Cl. This is what? Alkyl halide. So from alkyl halides or haloalkanes, you can say. So alkenes can be prepared from alkyl halides by heating with alcoholic potash, that is potassium hydroxide dissolved in ethanol. The reaction removes the molecule of halogen acid HX and therefore hydrohalogenation reaction. And this is also known as elimination reaction. So what happens here? See here, RH2C is there, RH2C is there, and then CH2 is there, right? And X is there. In the presence of alcoholic KOH, in the presence of what? Alcoholic KH, what will be removed from here? See guys, this X will be removed. So we will be having what? And this H will be removed from here. So we'll be getting what? RHC double bond CH2 plus HX. Getting my point? See, what happens is this X is more electronegative. X is more electronegative. Then this will try to pull the electron from this carbon. So there will be a negative charge will be here, right? And this carbon will be having the positive charge. Clear? OH is having minus charge, so OH will attack the positive center of the carbon. Clear? And then what will happen? Then there will be a rearrangement will be there. Clear? So there will be a formation of what? Alkene will be there. Clear everyone? How we can make this alkene? How we can prepare this alkene? Any doubt to anyone? So we are having what basically RCH2 CH2X is having. In the presence of alcoholic KOH, it will give what? RCH double bond CH2 plus HX. So if I will give you another compound, then can you make or not? Please tell me that. What do you say, guys? Will you be able to do? I'm going to give you one question. Then please tell me that what is the compound that you are going to get. Just a moment. See here. Without seeing this, you have to think about this and you have to react with this KOH and then tell me this. This is what? Alkyl halide. This is what? Bromopropane is there. This is what? Alkyl halide. Alkyl halide. When react with what? KOH. Clear? So what you will be going to get here? The double bond will be formed CH3, CH, double bond CH2, then KBr plus H2O. Clear? Okay guys, see here how this happens. This, see, one thing that you have to learn first, this is carbon, and here there is what? Halogen is there. So any functional group or any double bond or triple bond is there. So if it is attached with this carbon, then this carbon will be known as alpha carbon, this will be known as beta carbon, and this will be known as gamma carbon. Clear? Any doubt? So what is this alpha, beta, and gamma? Any doubt to anyone? So guys, what will happen? See, this carbon is more electronegative, right? This carbon is more electronegative. So it will try to pull out the electron of itself and carbon as well, right? And what will happen then? What will happen then? See guys. So it will try to pull out the electron, right? Then what will be going to get here? And this hydrogen is there, right? Actually, what will happen in this case? See, from alpha carbon, X will be eliminated, and from beta carbon, hydrogen will be eliminated. Because we are reacting with KOH. In this KOH, K plus is there, right? We are having what? K plus KOH, it means what? K plus and OH minus will be there, right? So here what we are having, this X that is having what? Minus charge will go to this K plus. And from here, the beta carbon, what will happen? This hydrogen will go to that OH. So we'll be getting what? There will be a vacancy will be there of what? Bond, right? So we'll be having carbon double bond carbon, right? Carbon double bond carbon will be there, and this KOH will become what? KB. That whether Cl or Br or I will be there, then it will be what? Kx. And the byproduct that we'll be getting is what? Water. So the ease of dehydrohalogenation of different halogenation is what? Iodine first. It is easy to remove iodine, then bromine, then primary or any secondary groups will be there. Clear? Any doubt to anyone? So guys, have a break of 5 to 10 minutes, then we will be back. Please have a note first, then take break only. Clear everyone? So we have seen that preparation of alkene, right? Now see here. Here we can see that, yes, guys, please turn on your camera. Yes, see here. In case of alkyl halide, can undergo dehydrohalogenation in two different ways. That alkenes is preferred, which is more alkylated, that is having more alkyl group, right? That is have more number of alkyl groups attached to double bonded carbon atom. This is known as Sedgwick rule. See here. This alkene, if you will be going to see, CH3, CH3, CH, Br and CH3 is there, right? Alcoholic KH we are having. Here we are getting what? CH3, CH3 double bond CH, right? And now, if you will be going to say this, so we are having what? CH3 group, right? Getting my point. So total number of CH3 group is what? That is 3. 3 CH3 group is there. We can open this chain as well. CH3, C, CH3, then again CH, and again we are having what? CH3. Getting my point. So here double bond is there, and again CH3 is there. So total number of CH3 that is attached to this carbon is what? That is 3. Getting my point. So 3 CH3 group is there, so more alkynated. According to Sedgwick rule, major product will be this. But if you will look into this carbon, see, there is double bond is there. Here there is what? CH group is there. So there is no directly attachment of alkyl group. So the major product will be this will be minor product. Less alkynated. So major product will be this. Getting my point? Now see here. From dihalogen. Dihalogen means what? X can be Cl, Cl, Br, Br, or ClBr. So there can be 2 halogen will be there. So vicinal dihalides. So dihalogen derivatives of alkanes in which 2 halogen atoms are attached to adjacent carbon atoms called vicinal dihalogen are converted into alkenes by heating with zinc dust in ethanol. See here. CH2Br is there, then CH2Br is there. So this is attached with 2 different carbon and carbon, Br and Br. One is gem is also there, right? So when there will be a gem, then when 2 halogen groups are attached in 1 carbon only. Getting my point? It is called as Wick form. Another will be called as gem form. So when it is react with Zn in presence of ethanol, so it will be giving what? Ethene and ZnBr. Now CH3CH, CH2Br, Zn in the presence of ethanol, it will be giving what? Propene. So this is ethene one, this is what? Propene one, and rest you are getting what? ZnBr2, ZnBr2. Clear? Now, so reaction of removal of halogen ClBr or I2 from dihaloalkane can form an alkene is called dehalogenation reaction. So halogen has been removed. So it is what? Dehalogenation reaction. Next is what? From alkynes. We can also prepare alkenes from alkynes. So alkynes can be reduced to alkenes using palladium charcoal, that is palladized charcoal, catalyst, partially deactivated with poison like sulfur compound or quinoline compound. Getting my point? And partially deactivated palladized charcoal is known as what? Lindlar's catalyst. So partially deactivated palladized charcoal is known as what? Lindlar's catalyst. Getting my point? So alkynes can be reduced to alkenes with sodium liquid ammonia called Birch reduction. So alkyne, there will be triple bond will be there, right? So triple bond will be there. Here there is double bond has been shown, guys. There will be a triple bond will be there. So here there will be what? Carbon will be there. So this carbon is having what? Triple bond. So in the presence of PD, CH2 or NaLiQNH3, it will give what? Alkene. Clear? Here there will be ethine will be there, so it will be converted into ethene. If propyne will be there, so converted into propene. Butene will be there, then converted into butene. So it may be noted that reduction of alkynes in presence of palladium supported over BaSO4 or CaSO3 and partially poisoned by S or quinolone, that is what Lindlar's catalyst, give what? Predominantly cis isomer. Clear? However, alkynes are reduced with lithium or sodium in liquid ammonia. Birch reduction give what? That will be giving what? Alkene only. Clear? Any doubt? No? So we can form alkenes from alkynes as well. Now next is what? From alcohols. See guys, alkenes are prepared from alcohols by heating with protonic acid such as sulfuric acid or phosphoric acid or at about 443 Kelvin temperature. This reaction is called dehydration of alcohols. Clear? See here. Ethyl alcohol in the presence of H2SO4 or H3PO4 will convert into what? Ethene. And this reaction is an example of what? Beta elimination reaction, because OH group takes out one hydrogen atom from beta carbon. Getting my point? So from alcohol. So guys, you have to learn that from where we can make this alkenes. So from alkyl halide, second is what? That you can see here from dehalogen or dihalogen you can say. Third one is what? From alkynes. Fourth one is what? From alcohols. So this is what? Alpha OH and hydrogen will be there. This is alkanol. In the presence of concentrated H2SO4, OH will be removed and hydrogen will be removed. From alpha position, OH will be removed, and from beta position, hydrogen will be removed. So that's why it is called what? This is called as what? Elimination reaction. This is known as what? Elimination reaction. Or we are also calling dehydrohalogenation. Getting my point? Dehydrohalogenation reaction or beta elimination reaction, simply we can say. Now see here, dehydration of alcohols occur on the following steps. So how this will happen? OH group will be here. So OH is having what? Lone pair, and H plus in the presence of acid will give what? H plus. Getting my point? So what will happen here? This oxygen is having electron. It requires what? Proton. So now you can see here, so this hydrogen will attack this oxygen. If hydrogen will attack this oxygen, so this oxygen will have to lose electron. If it is losing electron, it means there will be a development of positive charge will be there. So you can see here, oxygen is having what? Positive charge. And here it is having H, here we are having 2H. So this is known as what? Protonated alcohol. Getting my point? What is this protonated alcohol? So in the presence of acid, it is reacting. So it will be giving a what? Protonated alcohol. So alcohol gets protonated by the acids. Proton from acid attacks the electron rich side of the alcohol and gets attached to the oxygen atom, forming a protonated alcohol. So we have seen this protonated alcohol. And protonated alcohol loses water molecule to give what? Carbocation. So this will be removed as a water and giving what? Water. And this will be, if this will be removed from here, so this carbon will be called as what? Carbocation, because there is no electrons So you don't have to see for this 60 degree, guys. You have to just see what this water will be removed. So there will be no electron with this carbon. Only three side it is attached by three bond, but this bond is there is no bond. So it will be what hydro plus charge will be there. So carbocation will be generated. Getting my point? So you can see here. So carbocation has been generated here. Because what will happen? Oxygen will see if positive charge will be there. If positive charge will be with there with oxygen, so oxygen will try to pull out the electron from this carbon because oxygen don't want to be with positive because it is highly unstable when the oxygen is having the positive charge because it's already electronegative elements. If it is having positive charge, it makes unstable. So electron will try to pull out electrons from the carbon. Why from the carbon only? Because the oxygen is more electronegative. So if more electronegative, then it will try to pull out electron from the carbon. Is it okay, guys? So if its electron is completed, so it will pull out. It will be it will be removed out from here, and carbocation will be generated. So you can see here the carbocation has been generated here. Clear? Is it okay? Now, the carbocation is unstable at it and it loses proton from the neighboring carbon to form alkene. So as this carbon is what uh, unstable. So what will happen then? This hydrogen will lose its electron and to form what? Here there is a deficiency of electron. Here there is hydrogen is there. So if hydrogen is removed from here, right? So there will be a double bond will be generated. So you can see a double bond has been generated and H plus has been out. So carbocation is unstable and loses a proton from the neighboring carbon to form alkenes. So this carbon will be losing one proton. This H plus will be removed from here, and there will be a double bond will be formed. Getting my point? Clear? So in the similar way, propene is obtained by heating N-propyl alcohol with concentrated H2SO4. So if you will be heating this alcohol with concentrated H2SO4 and 443 Kelvin temperature, you will be getting propene. So it may be noted that secondary alcohols dehydrate under mild condition, while tertiary alcohols are very easily dehydrated under very mild condition. Thus, overall relative ease of dehydration alcohol is that is what there is ease of alcohol will be there. Dehydration will be there. So we have seen from alcohols, we have made what? Alkenes. Clear? Now, 3 degree alcohol, 2 degree alcohol, and 1 degree alcohol. So the ease will be what? 3 degree, then 2 degree, then 1 degree. Clear? Is it okay, guys? Now, this is alcohol in the presence of H2SO4 and 438 Kelvin temperature. It will be giving what? Propene. So from alcohol, you have got what? Alkene. This is what? Cyclohexanol. So in the presence of acid, it will give what? Cyclohexene. See, guys, cyclohexene. Sometimes the student think that this cyclohexene is benzene. This is not benzene. This is what? Cyclohexene. Although cyclohexene is not benzene. Cyclohex triene will be what? Benzene. Yes or no? If there will be triple bond will be like 3 double bond will be there at alternate position, then it will be what? Benzene only. So see, it will be what? Cyclo, like 6 carbon will be there, but 3 double bond will be there. So triene will be there. Right? Now, this is another alcohol. This is what? 3 degree alcohol, right? So if this 3 degree alcohol is react with H2SO4, right? Why this is 3 degree? Because this carbon is attached with another 3 carbon. So this carbon is 3 degree, so this alcohol is 3 degree. So it will be giving what? CH3, CH3, CH2 is there, right? So there will be a development of double bond here. Here there will be a double bond will be there. So this is easily dehydrated. 3 degree alcohol, easily dehydrated. H2O will be removed from here. Getting my point? Now, alkenes can also be prepared by heating alcohols with catalysts such as anhydrous zinc chloride, ZnCl2, or alumina, Al2O3. So if ZnCl2 and Al2O3, if it will be reacted with this alcohol, then you will be getting what? Ethene. So there are various processes by which you can form alkenes. I hope everybody is now comfortable that how we can prepare alkenes. So many methods are there to prepare alkenes, guys. Are you comfortable? So at least 5 to 6 methods I have shown you. Although your NCERT is having very less, right? But I have shown you so many methods to prepare alkene. Practice at your home. Try to understand. Write 2 to 3 times the preparation of alkane, the preparation of alkenes. Then only it will be, easy for you for your next year as well, because this will be coming again in 12th standard. Now we are going to see the properties of alkenes, right? So first of all, we are going to see the physical properties of this alkene. Physical state, that is an smell. The first three alkenes, ethene, propene, and butene, are gas at ordinary temperature. The alkenes contain 5 to 18 carbon atoms are liquid, while the higher member of alkene family are solids. So more than 18, you can see here, alkene containing 5 to 18 carbon atoms are liquid. More than 18 will be solids. Clear? Any doubt? Ethene is colorless gas with faint sweet smell. So smell will be what? Sweet. Clear? Now, about the melting point. In general, alkenes have higher melting point than the corresponding alkanes. Right? So alkene will be having higher melting point than alkanes. Right? This is due to the reason that pi electrons of the double bond are more polarized than sigma electron of the single bond. So if more polarization will be there, then more what will be there? Melting point will be there. As a result, intermolecular force of attraction are stronger in alkenes than in alkanes. So intermolecular force of attraction is more, so that it will need more melting point. Thus the melting point of alkenes are higher than the corresponding alkanes. The melting point and boiling points of alkenes in general increases with increase in the molecular masses. So if you are increasing the number of carbons, so what will happen then? It will be increasing. However, this do not show regular gradation amongst the isomeric alkenes. Trans alkenes have higher melting point than their corresponding cis alkenes. That we have seen. Trans will be having more what? The melting point than the cis one. Now see here. This is what? Cis one, CS3. I hope now you are very much comfortable with the cis and trans one. This is what? Cis one. So melting point is what? 134.2 Kelvin. This is what? Trans one. So it is 167.4. So trans alkene will be having more melting point than the cis one. Clear? Any doubt? Now see here. Boiling point. The boiling point of alkenes shows regular gradation with the increase in number of carbon atoms like alkanes. More the carbon, so there will be a more gradation will be there. In general, for each added CH2 group, the boiling point rises by 20 to 30 degrees. So more the carbon, more will be the boiling point. The branch chain alkenes, however, have lower boiling point than the corresponding straight chain. See guys, if you are having 4 carbon in a straight, it will be having more boiling point in comparison to branch one. Because the molecular formula remains same, but the structure has been changed. So the chain will be having, straight chain will be having more boiling point in comparison to branch chain. Clear? So however, lower boiling point than the corresponding straight chain alkanes. Amongst the geometrical isomeric alkenes, cis alkenes have higher boiling point. See here, cis alkenes have higher boiling point than the corresponding trans isomers. So in case of boiling point, cis will be more. In case of boiling point. In case of melting point, trans will be more. Clear? Now see here, cis 277, trans 274. Clear? Now, we have seen these things earlier as well. Trans butene. So this is what mu equals to 0. That is what they are having what symmetrical and unsymmetrical cis alkenes are polar, hence have finite dipole moment. So the there will be what dipole moment will be 0. Here there will be dipole moment will be greater than 0. So cis alkenes are polar and hence have finite dipole moment. So cis will be having dipole moment, but trans will be having 0 dipole moment. This is because the two dipoles of the individual bonds are on the same side and have a resultant dipole moment. Clear? So you can see here cis but 2 in dipole moment 0.25, but cis pen 2 in, see actually this is what trans. So if CH3 CH2 is there and CH3 is there, right? And here what H and H is there. So they are in what? They are what? They are trans or cis? They will be trans, guys. So if trans will be there, then greater than mu. 0 will be like mu will be greater than 0. Clear here? Am I clear here? Please guys, please tell me. Any doubt, then please tell me. Any doubt to anyone? Is it okay? So cis butene will be having what? That will be mu equals to what? That we have seen here. So dipole moment will be what? In case of cis will be, there will be more. In case of trans, there will be 0. Now, see here in this case, CH3 CH2 group is there and here CH3 group is there. So this is what? This is what? More molecular mass. We have taken this. So it is what? E or Z? What do you say? This is E1 or Z1? Who will be telling me? Z is what? Same side. E is what? Different side. So this is what? More mu. Now, similarly, unsymmetrical terminal alkenes such as propene and but1 have same dipole moment. So here you can see that what? We are having 0.35 CH3. That is what in this case. And H and H, they are having same, right? And here CH3 CH is there. So it will be having what? 0.35 almost, that is what 0.37D. So this is the same dipole moment because the polarity due to the alkyl group is not cancelled by the corresponding polarity of the opposite direction. So polarity has not been cancelled out here. Clear everyone? This is unsymmetrical alkene. This is not symmetrical one. Because here if you will be cutting this part, H and H is there. Here there is a different part. So we have done with this part, guys. I hope you have understood these things.